Hello friends, this is Devbrata Pramanik and you are watching my channel Physics Friends. Today we are going to find out the magnetic field produced by a circular current carrying loop at an axial point. Let we consider a circular current carrying loop of radius r and having current I. First we consider an elementary line segment dl on this loop. The position vector of the axial point P with respect to dl is r, and this position vector r makes an angle pi by 2 with dl. So, in Biot-Savart expression where we have a term sine of the angle between r and dl, here the term takes the form sine pi by 2. So the Biot-Savart law, according to the Biot-Savart law, the magnetic field at P due to dl takes the form mu naught I by 4 pi dl sine pi by 2 by r square is equal to mu naught I by 4 pi dl by r square, as sine pi by 2 gives 1. Now look at the figure. As Biot-Savart law has a term dl cross r cap, which is a cross product, and you know cross product always gives a direction, and the direction is along the perpendicular direction to both r and dl. So the elementary magnetic field produced by dl, that is dB, must be along this direction, which is perpendicular to both r and dl. If we take this angle as theta, then this angle also will be theta, and if we divide dB into its components, its horizontal component dB cos theta and vertical component dB sin theta, then considering the entire loop, all the dB cos theta terms will cancel out, because all these dB cos theta are in the horizontal plane. So the resultant magnetic field at P due to the entire circular loop must be due to these dB sin theta, and we have to integrate this dB sin theta. Now what about this integration? We have the term dV is equal to mu naught by 4 pi dl by r square. So dV sin theta is equal to mu naught by 4 pi dl sin theta by r square. If we integrate over this expression, we get like this. Now sin theta can be written as capital R by r. Sin theta can be written as capital R by smaller. So if we replace this sin theta in this expression, then we get this term. But look at the figure. For all these points, for all the points on this circular loop, the value small r and capital R are same for all these points. That is, small r and capital R are constant on this circular loop. So we can take them outside the integral. Finally, the integration turns to a function of only one variable dl, and integration over dl gives 2 pi r. So finally we get mu naught I r square by 2 small r cube, but r can be written as root over r square plus z square. Small r can be written as root over r square plus z square. If we replace small r cube, then we get this term finally. That is, the magnetic field at P will be mu naught I r square by 2 r square plus z square to the power 3 by 2, and the direction would be along the axis. Now look at the figure. If we want to find out the ratio of magnetic field at P and the magnetic field that of O. Then we will have like this type of expression, because mu naught I by 2 cancels out, and r square, mu naught I r square by 2 cancels out. So ultimately we get r square by r square plus z square to the power 3 by 2. This ratio turns to, and which is nothing but r by root over r square plus z square to the power 3, that is cos cube phi. So BP, that is magnetic field at P, is equal to B naught cos cube phi. Thanks.